Welcome! Today, we are diving into something that's at the very heart of organic chemistry, functional groups. If you've ever wondered what gives a molecule its unique power, well, think of these as the special Lego bricks of the chemical world. So let's get building.
Have you ever stopped to think about why two chemicals can be so different even when they look kind of similar on paper? I mean, take the acetic acid in your kitchen vinegar and the acetone in nail polish remover. At their core, they both have a simple carbon backbone, but their properties are just worlds apart. The secret to this whole puzzle? It comes down to one thing: the functional group. So what is a functional group, really? The best way to think about it is like this. Imagine a plain, flat Lego base plate. That's your basic carbon chain. A functional group is that one special, unique Lego piece, the propeller or the wheel that you snap onto it. It's just a specific little cluster of atoms, but it gives the entire molecule its identity, its personality, you could say. It completely dictates how that molecule is going to behave. Okay, but before we start snapping on all those cool, special pieces, we've got to understand the base plates themselves, right? Let's start with the most basic carbon skeletons out there, the hydrocarbons. So here's a quick breakdown of the three main types. First, you've got alkanes, like the propane you use for grilling. They only have single bonds between their carbons. We call them saturated because they're holding on to the maximum number of hydrogen atoms possible. But if you introduce a double bond, you get an alkene. It's now unsaturated because you could theoretically break that double bond to add more stuff. Then you kick it up another notch with a triple bond, and you get a superreactive, highly unsaturated alkyne. It's all about how those carbons are holding hands. And then there's this special case, aromatic compounds. Benzene is the classic example here. Instead of a chain, it's this incredibly stable ring of 6 carbon atoms. Think of it less like a standard base plate and more like one of those special circular Lego pieces that's just extra sturdy. It makes a perfect foundation for some really interesting chemistry. All right, we've got our base plates. Now for the fun part, adding those special bricks. And we're going to start with functional groups that are built around one of the most important atoms out there, oxygen. So let's say you take a simple carbon chain and you attach a hydroxyl group to it. That's just an oxygen and a hydrogen, then OH group. Boom, you've just made an alcohol. The most famous one, of course, is ethanol, the kind found in alcoholic drinks. That one tiny addition, that OH, completely transforms the molecule's properties. Now, what if we take that exact same OH group, but instead of putting it on a chain, we attach it directly to one of those super stable aromatic rings we just talked about? Well, now you've got a phenol. It looks so similar to an alcohol, but its chemistry is totally different. Phenol itself is a powerful antiseptic. So you see, where you attach the functional group matters a lot. Let's look at another oxygen group, the carbonyl. That's a carbon double bonded to an oxygen atom. And once again, its location is everything. If that C double bond O is sitting at the very end of the carbon chain, we call it an aldehyde. But if it's sandwiched somewhere in the middle of the chain, it's a ketone. And hey, look at that example, acetone, our nail polish, remember, from the very beginning. And this brings us full circle, right back to our vinegar. When a molecule has a carboxyl group, which is a carbon double bonded to one oxygen and single bonded to an OH group, it becomes a carboxylic acid. The prime example, acetic acid. It's what gives vinegar its sharp, distinct taste and smell. And oxygen's versatility doesn't stop there. It can act as a simple bridge, just connecting two carbon groups to form an ether. Or it can be part of an ester group. And esters are fascinating. They're the molecules responsible for so many of those wonderful fruity smells and flavors, like bananas, pineapples, you name it.
Okay, so that was the oxygen team. Now let's bring in another major player, nitrogen. And when we talk about nitrogen-based functional groups, we are talking about the absolute core building blocks of life itself. It all starts with a simple ammonia molecule, NH3. If you start swapping out its hydrogen atoms for carbon chains, what you get are amines. And this is so important because amines are a fundamental part of amino acids, which, as you know, are the building blocks for every single protein in your body. So what happens if you combine the two families we've just talked about? You get an amide. It's a bit of a mashup. It has a nitrogen atom bonded right next to that carbonyl group we saw earlier. And this link is incredibly stable and important. It's the peptide bond that literally stitches amino acids together to form proteins.
The nitrogen team also has some other heavy hitters. You've got nitriles with a powerful carbon-nitrogen triple bond. They're used to make things like superglue. And then you have nitro compounds, which are key ingredients in many explosives. As you can see, each group brings a totally unique and potent set of properties to the table.
So we've seen all these different Lego bricks, the oxygen ones, the nitrogen ones, but why does this all matter so much? Well, it all comes down to the unbelievable power of a simple swap. This right here is where it all clicks. Let's start with our plain, stable benzene ring. On its own, it's not super exciting, but snap on a single OH group and it instantly becomes phenol, a powerful antiseptic. Now take that exact same ring, but this time snap on a COOH group instead. All of a sudden, it's benzoic acid, a common food preservative. And that's the main takeaway. That's the whole story. By changing just a handful of atoms, by swapping one of these little Lego bricks for another, you can completely transform a molecule's function in the real world. You can go from an antiseptic to a food preservative. It's that powerful. You know, this is the entire foundation of modern drug design, of materials science, of so much innovation. By understanding these functional groups, chemists can literally design and build brand new molecules to do specific jobs. It really leaves you with a final exciting question. With an almost infinite number of ways to combine these chemical Lego bricks, what incredible new things will we build next?